All right, so welcome everyone to Jeff Thompson's thesis defense. Thankful for everyone that's here, and especially for our committee for serving on Jeff's committee and helping him through the process of constructing his thesis. I was looking through my emails and I noticed that this conversation between Jeff and myself was initiated by Jeff by an email sent on April 6th of 2021. So this is actually the 2-year anniversary of Jeff, thinking about this question after we talked about it in Stat 520. And I'm really proud of what Jeff has been able to do. All of this has been initiated by really his investigation and his thoughts about how to approach this problem. And I hope that you are enriched by some of the innovative techniques that he brings to bear. So without further ado, I'll pass it over to Jeff.
Thank you, Dr. Soare. That was very kind. Thank you, everyone, for coming today. Your support means a lot to me. I really appreciate taking the time to listen to me speak. I've run out of people on campus to corner and talk about it. So thank you. And thank you, my wonderful committee, for being here to support me and hear the defense of my thesis. So without further ado, let's begin. So my thesis is titled Approximating Infinity, and it's an investigation of the n is equal to 30 rule of thumb. So first of all, my thing isn't rendering properly. That's okay. An outline, and I apologize, I got cut off on the transition. It's a overview of what we're going to talk about today, the general roadmap of how we're going to approach this conversation and discuss n is equal to 30 rule of thumb. Yeah, great idea. If you have any questions, please know the slide number and please give a question at the end. I would love to answer it. The general roadmap is going to be as follows. So we're going to talk about the n is equal to 30 rule of thumb, just a general broad strokes conversation, discuss central limit theorem, how do practitioners determine normality, and then visual and descriptor methods. Then we'll talk about neural networks and their architecture and their performance, visual descriptor-based methods as well, testing the n is equal to 30 rule of thumb, some key assumptions, and then how we made the data / nonlinear regression, and then skewness, how it plays a role. And then you can't see it, but the conclusion and future works. So n is equal to 30 rule of thumb. So before we talk about that in depth, we have to talk about kind of the engine, the thing that drives n is equal to 30 rule of thumb. And that's the central limit theorem. And the central limit theorem states that if you have a sample, x1 through xn, and it comes from a distribution that has a mean and a finite variance, then the distribution function of the random variable, if you standardize it, converges to normal, standard normal, as n approaches infinity. Now, this then implies that there is a number that exists between 1 and infinity that is sufficiently close to normal, that approximate it well enough. And n is equal to 30 rule of thumb is that proposed number. It is a number that we consider large enough that it approximates infinity. And to give you an idea of what the central limit theorem is, I know we've all seen it before, we've talked about it before, but I have a brief visual that demonstrates it in action. So let me show you. So this is a GIF of the central limit theorem being applied, essentially. And each of these sample means we are taking from is the exponential with lambda 1. These are 200 observations of 1 sample mean, 2 sample mean, 3 sample means, so on and so forth. So you have x bar of 110, and it goes up, and it's going to go up to 200. And as you see, as the sample means increase, the distribution becomes more and more bell-shaped. And you have a p-value that's associated with the Shapiro-Wilk test. And then the dotted line is the theoretical normal distribution, and then the red line is the distribution that's been mapped to whatever data is actually there. It's a pretty neat little visual. I really appreciate it. And I think this really represents the CLT and especially how we use it in my thesis. Okay. So this is a potential origin of the n is equal to 30 rule of thumb. It goes all the way back to Fisher's work in 1925, almost 100 years ago now, where he proposed the t-table T critical values, where it goes from 1 to 30 and then to infinity. So, Fisher says in essence here, past 30 is close to infinity. So, we have the 30 approximates infinity here. And this is also seen across our discipline at large. We have conversations in the practitioner world where we have 30 being approximating large enough sample to approximate normality. In our textbooks, it is very, very, very common to say that 30 is big enough. We say that's the cutoff. So we have this convention that we are applying pretty indiscriminately. And so one important part of this discussion is understanding that normality here will be a classification problem, where it'll be a binary classifier, either normal or not normal. It won't be a gradient or a scale. It'll either be exactly normal or exactly not normal. And this is important for discussions as we go forward. So how do you determine normality, right? This is a fair question. There's two main ways. There's the visual methods, where you have, a QQ plot here on the left and a histogram on the right. And the other way is empirical methods that are descriptor based. Things like the Shapiro-Wilk and Jarque-Bera that use critical values and then p-values, right? Ways that we can empirically decide that this distribution comes from a normal distribution or not. And it should be stated that the classical tests have a very common through line of a hypothesis, right? The null hypothesis says that it comes from a normal distribution, and the alternative is that it does not come from a normal distribution. And this is important because it links into exactly the limitations. And while the classical tests are an incredible invention and something that are the cornerstone of our work, there are some things that they don't quite do perfectly. And let me talk about that real quick. You have sensitivity at high and low sample sizes. The null hypothesis is normal, which we showed before and we have on this screen as well. But that means the best we can do is fail to reject normality. You never accept it. We have insufficient evidence to reject, and we have insufficient evidence otherwise. We can't truly accept this condition. And we have this large problem where, we can't assert anything more than fail to reject. We can't truly accept it. And when a large amount of studies, or you have a lot of data, or you have an important part of your study is normality assumptions, this is a very weak assertion. And something that is often not stated very strongly, is not discussed enough, is this weakness. But when we saw this and we talked about this and we were coming up against these things, we thought, what could we do better? How could we improve? And so enter neural networks. So for our case, we're going to be leaning into and using Simic's work. We based some of our initial thoughts and processes in one of our networks based on Simic. He implemented normality testing through a neural network. And so some of the benefits of using neural networks for this context is they can be trained on any sample size. They can be trained and tested on any sample size. They're not sensitive to this. They don't have the same limitations of null hypothesis or alternative hypothesis. The assertions are much different. They can be trained and improved. There is no endpoint to a neural network. You can continually change and make it better and better and better and better. And they use pattern recognition, which is very similar to how we make decisions, which is an incredible benefit to be able to share a decision with the test you're using. So a little bit about what a neural network actually is, right? So this is a graphic of a basic neural network structure where you have Z is a linear combination from one layer into the next. They are the weights, Xi's are the inputs, and there's a certain inherent bias. And this essentially is a computational model inspired by the structure and function of neural systems like our brain. There's usually multiple layers, usually 3 or more, an input, at least one hidden layer, and then an output layer. And these include different neurons or nodes. And they're structured in a hierarchical manner, as you can see here. It's done by iteratively adjusting weights, and that's how it learns through the learning algorithms, excuse me. And this then uses a nonlinear activation function, typically ReLU or sigmoid to create new patterns or create patterns in the data. We also used this as a descriptor network, and we'll talk about that more in a second, but we also used we used two more networks for our study here. And we used the convolutional neural network. So convolutional neural networks take in image data and convolute it, and then max pool. So we're reducing dimensionality such that you can flatten the square image in our case and turn it into a similar network to the one we just showed you, where you have the fully connected layers and neurons. And this is quite interesting because we wanted to mimic this idea of empirical versus visual methods of approximating normality. So the network before was the empirical methods, the descriptors, and the convolutional neural network is the visual. And a few things about the convolutional neural network, you have a few equations that are worth mentioning. They're imperative, convolution, which is this equation shown here. I won't go into it too deeply, but this is how we're turning these images into a set of flattened descriptors. So you have the convolution operation and then the max pooling operation. And these two things in conjunction allow us to reduce dimensionality and turn it into a flattened layer. And so this graphic here is sort of trying to give a sense of the whole process of how we built the classifier, how we built these classifiers in general. So we took simulated data, right? We built the data set from normal and non-normal data sets, functions. We used, our norm for normal, and then I'll go into how we made the not normal data in a second. And then we use that one data set to be a list for descriptors and the other for visual. And then in order to train and test a neural network, we had to split that data, and we did a 70-30 split of the training data and then the testing data. And we use that testing data to validate how well our network did on the training data. And then we also would use k-fold validation to iteratively test the certain hyperparameters that we set for the models to see which combination was best. And then the last network we used is a combination of the two networks, a multi-branch neural network, where you have numeric data and image data as the two inputs that are then go into two networks, as in the descriptor-based neural network and a convolutional neural network that feeds into an interconnected, fully connected layers and activation. And this way, we're trying to simulate the combined input of visual and descriptive, which we hope to most accurately simulate how we look at normality. That's a lot, I know, and we're going to keep going into it. But from here, we're going to start talking about kind of how we made the data, because it's worth discussing, and it's actually quite non-trivial. So when you train a network of any kind, you have to have balanced data. You can't just pick things randomly. You must have some intention about how you construct the training data, and same true for our neural networks. So we needed to create normal data and non-normal data. Now, normal data is quite easy to make. You just have the normal function, you pick different means and samples and standard deviations, not a problem. But the non-normal data is much more challenging. To make a balanced non-normal data set, from the distribution functions would take quite a lot of work, and it's something that I actually would love to see done. But CIMIC was brilliant and used the Pearson family. And we followed suit. We followed the same idea. We used 30,000 samples, half and half, half normal and half non-normal. And then we used a 70-30 split for training and testing, same as CIMIC. So a little bit about the Pearson family. There are seven distributions, 7 families that explicitly account for the entire ranges of possible skewness and kurtosis. So that's what we're seeing here on this graph, is all possible ranges of skewness and kurtosis, and each range is associated with each wedge here is associated with a family, 1 through 7. we're going to talk about explicitly 4, 5, and 6. Type 1 is beta, because I don't really need to show much about this. We're somewhat familiar with beta. Type 2 is a special case of beta. It's that red line here, perfectly symmetric. Type 3 is gamma, as shown here. And then type 7 is this other line here, is a special case of type 4. So we're going to talk about 4, 5, and 6. I'll show them here in a second. And show you these things. So Pearson family type 4. This is a very complex equation. It's difficult to exactly see what's going on here, but this C is this equation here, and then this F is this equation here. It's quite long, it's quite involved, but it makes this very interesting and malleable distribution curve, which we need. And then type 5, this one has a lot more skewness and kurtosis. You can see it starts this, it can be this or this and get really flat. A little more simple. Still, all these functions are pretty complex to account for a large range. And then type 6, again, pretty complicated. Similar to the previous one, but a little more kurtosis. Okay. So what are our neural networks actually looking at, right? What are we passing to them to learn from? And so for our descriptor-based neural network, or DBNN, as I'll acronym it, is 16 descriptors, sample statistics that are passed to the network. So each sample they pass to it is broken down to 16 descriptors. Sample size is an N, sample mean, median, minimum value, maximum value, standard deviation, and quantiles 0.1 through 1. So the first to the 10th quantile. And so for ours, we used a architecture. We resulted on one hidden layer with 160 nodes with ReLU activation, and we used k is equal to 5-fold validation. The loss function was binary cross entropy, and that's true of all of ours. The optimizer was an atom with learning rate of 0.001. We tuned on accuracy, and our layer dropout was 0.4. This was distinct from CIMIC's network, which used 128 nodes, or excuse me, 100 nodes and 2 hidden layers, 110. But we'll get into that in a little bit. This is how our network did. So we tested and trained it on that data, and they're pretty exciting. We have an accuracy overall of 90.53, which is comparable to CIMIC's. We'll talk about that a little bit later, but false positive rate of about 16% and a true positive of about 97. Really excellent as far as we were concerned. Very, very heartening results. And then we did the convolutional neural network, right? Where we looked at histograms, where we passed a histogram of every sample. We thought, okay, what if we could, instead of just looking at the numbers, what if we looked at the actual picture? What if we saw the visual representation of the data and we passed it to a neural network? And so this histogram is what the convolutional neural network would quote unquote look at and make a decision on. For those who are curious, this is a 256 by 256 pixel image. And then here's the architecture. It's a little hard to communicate architectures of convolutional neural networks, but it takes in a 256 by 256 with one layer. It's black and white image. It convolutes 32 filters with 3x3 kernel, ReLU, max pooling 2x2, and then it goes 64 3x3 ReLU, 2x2 pool, dropout rate 0.25, and then it flattens, and then we get to a standard, feed forward neural network with a dense of 128 ReLU, dropout 0.5, and then output of a dense 1 in sigmoid. And I apologize for this really dense information. There's a lot to communicate in a very short time. So thank you for sticking with me on through this. And then here's how we did. So notice that the accuracy was 0.8, or 89%, worse than the descriptor, and we'll get into that in a minute. A false positive rate of about 18.4, true positive 96.73. It's worth mentioning here that this was an extremely computationally dense thing to test. I had many nights where I would let my operation run and it would just crash in the morning. I'd wake up to having it run for several hours for it to just have been broken. My cat would have pushed the computer over or stood on the keyboard, or simply something would have gone wrong. It took quite a lot to get this thing to go. And it's a product of a lot of love and hard work. This exists. And then of the last network is the multi-branch neural network. So the multi-branch neural network takes in, the two kinds of data and then the two networks. And then what makes it happen is concatenate layer, which concatenates the outputs of the feed-forward DBNN and the convolutional neural network, the CNN. And then from there, you have two hidden layers of 120 nodes each and ReLU activation. There wasn't any k-fold validation for this because of the limitations of my computer. Again, the CNN didn't get k-folds either because of the limitations, neither did this. That is something I would love to pursue, is optimize these algorithms a little better. But this is how it did, and it still did quite well, all those limitations notwithstanding. Overall accuracy of 90.67, false positive rate of 15.53, and overall true positive rate of 96.87. It had the highest accuracy of the three models we tested. So for a little bit of an apples to apples comparison, just to see what we're talking about here and what we're dealing with and how well these did in comparison, I did a confusion matrix for the Shapiro-Wilk test, which is commonly considered the highest power classical test. And this is how we did. Pretty well. We had a overall accuracy of a little bit higher, false positive rate, a little bit worse, true positive rate a little bit higher. So very comparable. We did very close, if not maybe a little better, but be careful what I would say about that, but very comparable to a very strong and powerful test. And notice these is both the descriptor-based models and both descriptor-based representations of the data. So it's a pretty apples to apples comparison when we're talking about these two things. Oops, too many clicks. Okay, so as promised, I want to talk about CIMIC's work. So here are two graphs of representing the data that was stimulated. So on the left here, we have CIMIC's work, which encompassed a really large range of skewness and kurtosis. The skewness that CIMIC used was -30 to 30, and a kurtosis of over 300,000. And so we saw this and we thought, well, this really represents a lot of very obvious results. They are so obvious that you wouldn't really need a neural network or any kind of test to determine whether they're normal or not. The skewness of 30 is extreme, to the point of almost non-useful. So we wanted to restrict the training and testing set to better represent data that you might actually see in the world, a little more corner cases, right? So we restricted the kurtosis to -10 to 10, the skewness from -10 to 10, and the kurtosis from 300. We also kept it inside of the band of normal between kurtosis 0 and skewness 3 is that line, and that represents normality. So what we're trying to do here is make the test much more difficult to pass, such that the classifier would perform better on real world data. And as it shows here, we have an accuracy of 90.53 on ours, and CIMIC's was 90.47. So very, very, very comparable, even though our test was much harder to pass. There were much fewer very obvious cases, which is really encouraging. Okay, so before we go on and before we finish the preamble here, I want to talk about really briefly why we chose the convolutional neural network, because that is the network that we chose going forward for the testing and for the analysis of determining the n is equal to 30 rule of thumb's validity, is the CNN. And there's a lot of information, so bear with me here, but what I really want to highlight is this line talking about the CNN. This is the false positive rate per distribution, and this is tested over the same parameter space and sample size that we did for the rest of the study. We'll get into that later. But this is showing that the false positive rate for the CNN was particularly low on most of the distributions when individually tested, which is really important. That's that's how you use these tests, is on individual distributions. You don't tend to be given a shotgun of them all like randomly. You generally deal with one distribution at a time. And this is kind of how we wanted to use and address how well these distributions did, is how do they do per distribution? Now, it did fairly poorly, didn't do the best on beta. It did pretty well on exponential. It did very well on geometric. It did pretty well on gamma, the best on chi-squared, the best on binomial, and the best on Poisson. So we felt that even though its accuracy wasn't the highest, it still performed very well per distribution, well enough that it deserved to be the distribution we chose. So there you go. Okay, so with almost 30 minutes of preamble out of the way, let's start talking about actually discussing the topic at hand, testing the n=30 rule of thumb. We're going to start this discussion by establishing a hypothesis, talking about a key part of our logic and reasoning on how we made these assumptions and why we did what we did and how we can justify what we did. So when you're saying that n=30 approximates infinity, we're saying that that is universally applicable. It is saying that the CLT is working. It is saying that sample means, when you have a sample size of 30, sample means should be normal at this point. It should approximate normality. So whether you start with positive skewness, negative skewness, extreme kurtosis, negative kurtosis, it should not matter. The n=30 rule of thumb should be strong enough to overcome any of these disparities in the parent distribution. It should end up being normal, no matter what. And this is really important, is key that is very clear. So we tested 7 distributions: the Poisson, the beta, the binomial, the chi-squared, gamma, geometric, and exponential. And we tested them at these sample sizes and these parameter ranges. Now, note for gamma and beta, those are 2 parameter models. They were tested over this range for both parameters, so it's even. So for beta, alpha, and beta, they were both 0.1 to 5. The reason these sample sizes are different has to do with how long the distribution took to show a pattern, and before we established a threshold of normality. And we'll get into why that is, but this is mostly limited because of the computing power. It took a lot for my computer to make these samples. It took like 8 hours to generate all this data. And to try to reduce that load, I tried to limit how far it was. This all showed a pattern far past this data, but I wanted to not have them all be 500. And you'll see that in the graphs as we go forward. Also note that the parameter ranges for several of these distributions are truncated. That's intentional. Several of these distributions converge normality in their parameter space, like Poisson, chi-squared, and even gamma. And we wanted to mitigate that effect, and we wanted to isolate just the sample size. And how does the sample size affect the convergence of distribution? So we would try to limit Poisson and gamma and chi-squared to smaller values of their respective parameters, so we could limit that effect. So the way we tested is we had an omnibus test, and basically what we'd see is a sample mean, sample means were passed to these 4 tests, and each test would report a yes or no, basically. So it would be the Shapiro-Wilk, the Anderson-Darling, the Jarque-Bera for the 3 classical tests, and then 1 convolutional neural network that we created, that we trained and tested ourselves. In this way, each sample would report a percentage between 0 and 100% to pass based on these 4 tests. Okay, so this is maybe the most confusing aspect of my work. So try to bear with me here. I'm gonna do my best to explain this. I found this to be the most challenging aspect of the discussion. If you find yourself a little lost, I apologize, that is not strange. So let's talk about how we made the data, and we'll go at it one by one. So we're trying to isolate sample size as the effect, right? So we made the data by looking at sample size 1 for Poisson. This is our examples in Poisson. So sample size 1 with the parameter lambda 1, 200 repetitions, and those 200 repetitions were passed as a single sample to the omnibus. So we would report 4 yes, nos. And then sample size 1, lambda 2, 200 repetitions passed to the 4 tests. And then that so on and so forth, all the way up to n is 1, lambda 10, 200 repetitions, 4 yes, nos. So for sample size 1, we would have a total number of yeses divided by the total number of iterations. So 4 times the number of parameter values. So it'd be 40 in this case. So you'd have 40 yeses and nos. And the 200 repetitions here is intentional. Through our research and the literature, it seemed that remember the classical tests are very sensitive to sample sizes, and 200 seemed to be the upper limit of what we could pass to the classical test without them getting too sensitive. So once we did that, and so we repeated for between 2 and 50, we ended up with something like this. We had, for sample size 1, we would have the number of yeses divided by 40, so some percentage of divided by 40, and then we have a percent passing, and that was done for each sample size. And each of these ends resulted in 1 data point, which looks like this. So you have Poisson, and on the x-axis you have sample size, and on the y-axis you have percent passing. So each data point here corresponds to a sample size and a percent passing. Now, what seemed to us since we plotted this was, well, there's some kind of relationship here. There is some nonlinear relationship, it looks like. And we did some nonlinear regression and found that the log logistic model performed quite well. So the log logistic model is a very uncommon model as far as what you might come into in a normal class, but we defined it as this, or it was defined as this for our package. 1 over 1 plus e to the b times log of x minus log of e. Now note, b and e are both coefficients of the model. E is not the natural number e. As confusing as that is just the parameterization used by the package. Also of note here is the log odds, which is really it was really nice that it worked this well, is you ended up with x over e all raised to the b. And this equation is saying that how we can interpret the b coefficient, and it just says that as sample size increases, x, the odds of passing, approaches 1 proportional to the absolute value of b. So as b bigger, the sample size, as sample size increases, we have a higher likelihood of passing, which is the general pattern that we observe. So we tried this model for all the distributions, and we found it worked really quite well, actually. So here's the same graph of Poisson, same scatter plot, but with a not log logistic curve, and reported an RSE, or residual squared error, of 0.07, which is a moderate to strong fit. And so, as promised, we have the RSE and the log logistic model fitted for each of these distributions. The RSE is fairly low for all of them, the highest being geometric of 0.08, and then 0.07, and then 0.06, 0.04. You have many values that end up being below 0.05. We have 4 values below 0.05 and 3 just slightly above. Also note that all the coefficients here are significant at the 0.001 level. All the coefficients are significant, which is very heartening. And all the b coefficients are negative, which allows us to make those log odds interpretations. Now, one of the benefits of having a log logistic model here is that we can use it to answer our question. We can start looking at the question, using it to help us figure out what is good enough. How do we determine if n is equal to 30 rule of thumb is good enough, right? So we thought about this back and forth, and we had a lot of discourse regarding what consists of good enough. Is 80% threshold working? If 80% pass rate was good, 90% pass rate was good, 70%. We said that a 90% pass rate was good enough. 100% seemed far too critical, and 80 seemed a little too weak. I went with 90. That felt like that was comfortable for us to say this was a good enough rule of thumb. That if it was 90% of the time it was applicable, that was sufficient. So to that end, we're proposing this. We're saying that if the n is equal to 30 rule of thumb is applicable universally, then it should correspond to about a 90% pass rate on average. So if it actually can work as a criteria, so you can actually determine normality with this, the criteria, 90% should be applicable. So we took the values from the log logistic curve. We took those theoretical values and used that as the comparison. So whatever corresponded to a 90% pass rate, that was the n that you would draw on it. And that's what we'll show. We'll show that on a graph. So we're comparing these two values based on the log logistic curve. So Poisson, the same graph we've shown a couple of times now, but this time there's two vertical lines here that correspond to the n is equal to 30 value and then a 90% pass rate. So here, the 90% pass rate was below 30. It ended up being about 26. Pretty heartening, saying that maybe the n is equal to 30 rule of thumb works for Poisson. This is beta, not quite working as well. You have a 90% pass rate closer to 98, much higher than 30. Exponential, you have 147, quite large. Binomial, 80, much bigger. And then chi-squared, again, much bigger at 61. But notice that the pattern here has been very consistent across the board. So here's the summation of all that information. You have a n is equal to 30 rule of thumb versus the 90% pass rate. So you're comparing n at the 90% pass rate as the first row, and then n is equal to 30 with its corresponding pass rate in the second row. And this is just reminding you of the parameters that we used. So this has a few interesting things to talk about pretty briefly. We mentioned a couple of these n values. The other part that's fascinating is the percent passing corresponding to the n is equal to 30. And several of them had 80%, which depending on your proclivities may be good enough. But I really want to highlight two distributions. One is exponential, which I showed, where a 30 sample size corresponds to a 62% pass rate, which is better than a coin flip, but not by a whole lot. And then geometric, which the value of 254 was a 90% pass rate, and the sample size of 30 was no better than a coin flip. Is 50% pass rate at sample size 30. So there's a large disparity here between these sample size 30 and these values. Does that mean that we should just throw the rule away? Well, not quite. There's something we need to talk about first. Skewness. So skewness is integral here, and we found the Berry-Estine theorem, which is essentially saying that the difference between a function g of n and the standard normal distribution is bounded by some constant c and sample size and skewness. So you have skewness here as a clear factor, as a clear determinant of the bounds of this function. So it's clearly playing some important role along with sample size. And so we thought, what if we could look at skewness? What if we looked at skewness ranges? So a quick note about skewness values. 1 or more is considered highly skewed. 0.5 to 1 is moderately skewed, and 0 to 0.5 is low skewed. These are just standard, generally accepted ranges of how you measure skewness. So with that in mind, we plotted the theoretical values of skewness across these parameter ranges for what we tested. Notably, two things about this graph. One is beta is missing from it. It has a 2-parameter model that I couldn't seemingly fix, and it didn't really represent very well. And same is true of binomial, but I fixed it at the largest possible skewness I could to demonstrate the furthest range it would have. This isn't the true of every parameter combination, but this is the most dramatic skewness it would have. And what this is trying to say, and what I'm using this graph for, is to demonstrate the wide range of skewness and the levels of skewness that each distribution tends to attain. So I'm colorblind. So if I get one of these distributions wrong, please forgive me. I've been told this graph looks quite nice. I apologize in advance. But what's important here is the couple things. One are the two, offenders from the previous table, right? We have geometric here, which starts at about 2 and just shoots up, right? It gets really large really fast. And then exponential. Exponential stays at a constant 2, independent of the parameter space. It just is 2 forever. And then you have the chi-squared, gamma, and Poisson. And you have them stacked on top of each other. And you have ones that stay in the low ranges here between, in the moderate skewness range and the low skewness range. And then you have above the very high skewness range and the moderate range, and then in the very, very high skewness and the moderate. So these, when compared to the table, correspond pretty well on the sample sizes that correspond to pass rates. The higher the skewness we saw on the table, and if we went back, we'll see that more going forward, the larger sample size required to get a 90% pass rate. So it's no wonder that these two performed the way they did. So let's regroup here for a second. So we know a few things. So the n=30 rule of thumb shouldn't be applied indiscriminately. That's pretty clear. We saw that the distributions didn't attain a 90% pass rate when applied equally across the board. The parameter spaces should not be accounted for equally. We have to account for something, and that something seems to be skewness. There's a major factor here is the skewness profiles. And so what we did with that in mind is looked at 4 skewness ranges, and the ones we kind of talked about: 0 to 0.5, 0.5 to 1, 1 to 1.5, 1.5 to 2. We did break all of these distributions and data down by these skewness ranges, but for argument's sake, and time is a real factor, we're going to talk about 0.5 to 1. A couple reasons. One, this is the most interesting range. It is the most corner cases. It represents moderate skewness. So you have things that are most corner cases and the most overlap. So you have a comparison of coefficients in RSE. So this is the same thing we saw before. The RSE changed in increase, but it didn't change dramatically. And these all stayed at a significant level. I'm running out of time, so I'm going to try to hurry up here. You have Poisson skew, similar distribution, and the N changed from about 26 to 33. Beta did much differently. You have an N is equal to 26 now, so it's below the 30 pass rate, and it maintained a similar representation of shape. Binomial didn't change dramatically. It reduced quite a lot, but it didn't shift its position. N is equal to 53 here. Chi-squared ended up with below and ended up with N is equal to 21. So, without saying, with showing it here in these two side-by-side comparisons, the N is equal to 30 versus 90% pass rate for the skewness profile of 0.5 to 1, and then the generalized one is compared side by side here. And you can see, there's a lot of information, I know, but you can see here, by and large, the N is equal to 30 rule of thumb works fairly well. If you have a skewness profile of 0.5 to 1, the only offender that really failed was binomial. And, I would be remiss to call a rule terrible for only failing at a, 7% below what he expected. Quite encouraging, quite interesting, and honestly in line with what we would have expected along the skewness profiles being more symmetric. Vastly different too. So what does all this mean? Let's sum things up. So what can we say about the N is equal to 30 rule of thumb? Well, we can say that the rule is not perfect and it shouldn't be treated as such. It's a guideline and a suggestion, certainly not a criterion for determining normality. It should be treated with care. It is applicable when skewness is not too high, and 30 works as a placeholder, but very much that, a placeholder. It's meant to be delicately used and not applied blindly. Be very careful with reliance on broad generalizations. They are dangerous, they are alluring, and they often get you in trouble. So the key takeaway, the thing that I really want to make sure everyone is left with today is the N is equal to 30 rule of thumb is not perfect and should be more considered the N is equal to 30 provided not too skewed rule of thumb. And even then, reliance on these broad generalizations should be discouraged in some regard because no one answer works for everything all the time. Nuanced approach is always best. And as far as future works are concerned, we could write a bunch on this. I have so much I would love to do with this work. I want to improve the training data for the neural networks to better represent real-world applications. So try to make data that is more representative. I want to make the multi-branch neural network excellent, make it the best per distribution. And I think we could do that with some better computing power. I want to investigate different parameter ranges for different fields, different work focuses on different distributions and focus more on that than just the theoreticals. And then try to find what point Poisson, gamma, and chi-squared approximate normality. It's commonly accepted that they converge in parameter space, but what is that value? Where is the cutoff? And then ultimately release an R package that has the functionality of my thesis and disseminate it to the public. Thank you so much for your time. There's not much else I have to say. I appreciate you listening to me for this long, and it was a pleasure to be here.